Welcome to this series of videos on digital audio effects processing. In particular, we'll be looking at this system, which is a digital audio effects processor for the electric guitar. Here you can see the test setup featuring a power supply, the system, and this Analog Discovery Pro by Digilent, which is a mixed signal oscilloscope function generator, as well as logic analyzer. And we're using this system to discover digital signal processing and also has to test and analyze these systems and algorithms we are creating. In this first video, I'll give you an overview of what this video series will be about. We'll look at the hardware platform where we'll be using or implementing these audio processing algorithms. We'll look at how the software is set up, starting with a basic code structure, how the codec is set up, all the drivers and so forth. I'll also explain briefly what double buffering is and why we need it. Then we can move over to filter implementation, which is the first part of our audio processing effects. We'll look at real-time, variable, high and low-pass filters, as well as a simple volume control. Then I'd like to show you some practical real-world demos using our filter implementation. We'll do a system analysis and tests using the Digilent ADP3450 mixed signal scope and function generator. We'll look at the time domain characteristics, frequency domain, and so forth. I'll also show you this live with some audio via guitar and an amplifier. Thank you very much to Altium for sponsoring this video. If you'd like to give Altium Designer a try for yourself, they're offering a free trial if you go to altium.com/YT/Phil's Lab. There's a few Altium videos on my channel as well as KiCad. If you'd like a complete walkthrough of Altium, for example for creating an STM32 based PCB, I'll leave a link in the description and you can check that out for yourself. Thank you also very much to JLCPCB for sponsoring this video. I actually had the mixed signal guitar processing effects board produced and assembled by JLCPCB. I'd like to make this series because I have a huge interest in electronics and audio as well as digital signal processing. So I'd like to show you my way of how I implement digital audio effects in real time using the C programming language on an embedded platform. And the platform we'll be using is this one here. Essentially it's a guitar effects pedal, but inside I'm using my custom GDSP core, which is an STM32 F4 based signal processor with an audio codec, analog front end, and so forth. We have an audio input from a guitar and an amplifier output, various controls, and a foot switch to turn the effect on and off. In the series, I'd like to explore several effects, starting with IR filters, FIR filters, for example for equalization, distortions and overdrives, reverbs, delays, noise gates, compressors, and so on. And we'll be using this STM32 F4 based guitar effects pedal. If you'd like to learn more about the mixed signal hardware design, and this is a board I also designed in KiCad, I've recently released a course on the Federal education platform with mixed signal hardware design at its focus, where you'll learn to design pretty much a system like this, all the way from part selection and system requirements to getting the board manufactured. You can purchase the course via Federal Education, and I'll leave links in the description below. Here's an up-close view of the hardware platform. As you can see, this is a Euro coin in comparison, so it's pretty small. It consists of an STM32 F4 microcontroller, which is very powerful, has a floating point unit, various goodies for digital signal processing. We have some control inputs where we can connect potentiometers, switches, and so forth. Serial wire debug connection, USB where we could stream audio data. This codec over here, which is an ADC and DAC for audio combined. And this analog front end, as well as some power supply section over here. All in all, this board then lets you connect any type of connectors and house it in any housing you want because of its small size. And I've chosen to put it into this guitar effects pedal unit. Just to further help the understanding, here's a system block diagram. We have the processor as our core, power supplies which generate 3.3 volts for the digital supply, 3.3 volts for the analog ends, for example the front ends, and part of the codec. We have USB for data streaming, serial wire debug for debugging. We have ADCs on this processor which allow us to read values from potentiometers, switches, and so on. The way we interface with the codec is in two ways. One is I2C, which is used to configure the codec, set sample rates, bit depths, and so forth, and one is I2S, which is very similar to SPI and is the way we stream DAC data to the codec and ADC data from the codec to the processor. So we stream this data from the codec back to the processor. The processor will apply some sort of effects and send it back via I2S to output it via the analog front end. We record data essentially from the guitar. We have a fairly high input impedance of 100 kilo ohms. We do some filtering and processing in the analog front end and into the codec. And on the other end, we have a low output impedance of 100 ohms, again, analog rear end, so to speak. And that goes to, for example, a guitar amplifier. This design was made in KiCad, and I actually made this quite a while ago, and I have had some revisions. So this is quite an old design, but it still works for the purposes of this video. Let's just briefly skim over it. We have the microcontroller section, which is a standard STM32 F4 microcontroller, crystal oscillator, and so on. power sections, we have a switching regulator for the digital supply, LDO regulator for the analog supply. We have the codec over here, which essentially connects our analog world to a digital world to the processor, and we have some sort of very simple analog front end. Now keep in mind this is a very old design and as basic as it can be to fit on the board space. And here's the PCB in KiCad. As you can see, it's a pretty cramped design, and it measures in at about 35 by 60 millimeters, so it should fit in most enclosures. Now that we've looked at the basics of the hardware and what it can do, we need to move over to the software side of things. And there's some initialization we have to do, and I've written most of the code for you so we can focus on the more interesting aspects. We don't want to focus on writing drivers, we want to implement actual effects and see something come out of our hardware, so to speak. I'll be using the C programming language and also STM32 Cube IDE. Before you continue with this video and you're not too familiar with STM32 or writing firmware for these devices, I have an STM32 firmware playlist on my channel which will teach you the basics of writing firmware and the basics of STM32 Cube IDE, as well as a lot of DSP content telling you how to write FIR filters, IIR filters, the Z transform, and things we will be using over and over again in this video series. So I'd strongly encourage you watch them before you continue with this series. Our firmware essentially has to do four main things. As I said before, we need to initialize this codec, which contains the ADCs and DACs, and this is done, in this case, via I²C. For example, we have to set the sample rate, which I set to about 48 kilohertz. We need to set the bit depth, which I believe I set to 16 bits, and we need to set hardware filters. For example, the codec might have some anti-aliasing filters or its own digital signal processing, which you can enable via I²C. Secondly, we need to start the audio data streams, and this is done via I²S, which is very similar to SPI, and I'm also using direct memory access, which is DMA, and this really helps offload the CPU. Essentially what I can do is use DMA to stream data in the background while the CPU is processing and applying our algorithms to our audio signals. So our transmit stream via I²S and DMA will be to the DAC, so our output, and our received stream will be gathering data from the codec's ADCs. Nicely, STM32 and the processor we're using has DMA callbacks. We can let this DMA gather data and send data in the background, and once this has been completed, we will get some callbacks essentially telling us, okay, it's done now and you can do some processing. And we get that for complete and half complete, so RX and TX, and then we can just set flags and we can read the flag somewhere else and then process our data. So after we started the audio streams, we need to start ADC control readings, and the ADC in this case is from the processor itself. So these aren't suitable for audio, but they're suitable for reading, for example, control signals from potentiometers, reading the voltage across a resistor, switches, and so on. And again, I'm doing this via DMA to offload the processor so we can focus entirely on processing our audio data. Again, we have a DMA callback that allows us to then process the ADC readings coming from these control signals. Now, these control signals we will use to, for example, change volumes. We can change filter parameters on the fly, for example, changing the cutoff frequency, changing a Q factor, changing the reverb, delay times, and so on. So this is incredibly useful to have on a system. So once we've gathered our control signals and our data, we actually need to process that data, and to me that is the most interesting part and what this series will be focusing on. So once we have data received via these callbacks and flags, we need to check the flags, and it's the I²S and ADC streams. We will process the data using what is known as double buffer. We'll look at briefly what that is in a second. Then we need to process the control signals to change our effect parameters, and that's pretty much it. I briefly mentioned double buffering, and if you do a simple Google search of what double buffering is, you can see it exists in graphics, but also in audio or any type of heavy processing. For example, this page on EE Times gives a nice description of fundamentals of embedded audio and also on double buffering. So essentially for our input buffer, for example, we are using the DMA stream to fill that in from the ADC data into one half of this buffer. The other half of this buffer is being used for our processing of our audio signals and then fed to the output buffer. Once we are done with processing, the DMA stream will then fill up the other side of the buffer, which has now been used already, and then flip-flop between them. So every time we're reading in, we're not using that part of the buffer to actually process. So always switching and making sure we're being very efficient with our processing and also filling our data and retrieving our data. And this works both ways for the TX and RX streams. So this was a very vague description, and I really recommend that you read this up both on the EE Times website and also just on Google, and I will leave relevant links in the description below. Here we are now in STM32 Cube IDE, and I'd briefly like to go through with you what I've already written for the firmware, and then we'll move on to actually implementing some filters and seeing the results and analyzing the results. The first thing I always do is take over the pinout from my KiCad or from my hardware and put it into STM32 CubeIDE. So you see I've selected various analog to digital converters, which will read my potentiometer values. I have my I2S signals over here, which connect to my codec, USB, serial wire debug, as well as some LEDs and some various other signals, I2C and my clock. Then I need to do my clock configuration, so I have an external oscillator at 16 MHz, and I'm running my MCU at 168 MHz, which is the maximum it can do. Now in my main.c file, this seems a bit complex, but essentially if you remember the presentation slides, we only have 4 steps. We need to initialize the codec, and I've written a driver, or a very, very simple driver in this codec file up here. We need to start our data streams, and then we need to do the processing. So let's go through that. So I've included my codec file. My codec driver is very shoddy and very simple just to get this up and running. So I'm doing software resets, I'm setting PLL values to make sure that I'm getting the right sample rate. So I'm setting my sample rate to 48 kHz, and this will be important later for processing. I'm unmuting the various channels, powering up the codec, and so forth. And all of this I've done via the help of the datasheet. So the first thing I then do after all the peripherals are initialized is I initialize my codec and I wait a bit to let it settle, very loosely speaking. We'll come to this later, but then I initialize my effects, set my output volume, and then I start my data streams. So I use this here, which is a transmit receive command, and I'm using the hardware abstraction layer provided by STM32, starting my DMA data stream and filling in my buffers for the DAC data and ADC data. And if this works out for both for ADCs and for the codec, then I will start my sampling rate timers. And I'm using a timer to trigger the reads, for example, of my ADC at about 100 Hz or kilohertz. This timer for the ADC is for the control signals, and the control signals don't have to be sampled that often because I, as a human, am changing these, and I'm changing them, once in a while. So we don't have to sample the control signals, for example, from the potentiometers or switches too fast, so 100 times a second is more than enough. So once we are okay with starting the data streams, we do our processing and our while loop. Before we can process, however, we need to do our double buffering, and this happens in these I2S callbacks over here. I will leave a link to a video below in the description that'll teach you more in double buffering, also specifically to STM32. And this is the kind of structure one would have to implement. Essentially, rather than moving data, you're moving pointers around depending on if you're receiving, transmitting, or processing. For the ADC, we don't need to double buffer. This is the ADC of the control signals, and essentially I'm just converting my raw ADC readings to control settings between 0 and 1. Our main processing function is called process half because essentially we're just processing half of our buffer. Again, this is to do with the double buffering. We have left inputs, we have right inputs because it's stereo, and left outputs and right outputs. Now, because I'm using this in a guitar effects pedal and guitar effects are typically mono, we'll just be using the left input and the left output. And this process half function is our main processing function and where we will be implementing our filters and our code, or at least calling them. Very briefly, we make sure that during that time we are processing that the control signals do not change. So we indicate that with this flag to make sure we don't get any strange artifacts that while we're processing, maybe the control signals change and that will mess up our sound. So we loop through half of the buffer. Starting with the left channel, we get our ADC input, that is the ADC from the codec, and convert that from an integer to a floating point value, and then do some sort of scaling. And this depends on your codec and the way you're reading it in. I prefer working with floating points. It's less efficient, of course, but if we're just demonstrating various algorithms and we're not too concerned about speed because we have enough processing power, this is the way to do it. Work with floating points, it'll make your life so much easier. Then we, of course, have to compute our new output sample, and we'll look at how to do that in a second, and then convert it back to a signed integer to set the DAC output in the buffer. We do the same thing for the right channel, and that's pretty much it. So what we need to do in this series is compute the new output sample, and this will depend on if we're doing filtering, if we're doing reverbs, delays, distortion, and so on. In this video, I'd like to show you low and high pass filters. I understand this is a pretty vague explanation of this code, but it's basically to give you an introduction and overview of what parts of the code you will need. So if you'd like to follow along, I will leave code in the GitHub repository and I'll leave the link to that below. In this series, we are simply focused on actually then writing the audio algorithms rather than writing the drivers. So I'll give you this framework without much explanation, but if you have any questions, please leave them in the comments below. What we'll be implementing today are first order low pass and high pass filters. Now I have a video on my channel that goes in far greater detail of how to derive filter models from analog prototypes, but I will just run through the basics in this video. In essence, we'll be using this RC prototype filter, which is an analog filter as a prototype, and then moving over and discretizing this to give us a difference equation that we can then implement in software. First thing we have to assume is that we have equal currents through this resistor and this capacitor. We have a voltage source on the left, which is our input voltage. We pass this through our filter, and we take the output across this capacitor over here. So again, assuming equal currents through the resistor and capacitor, we can use Kirchhoff's current law to form a differential equation. Differential equation then turns out to be this one over here, so RC times dVout by dt plus Vout equals Vin. This, of course, is in the continuous time domain, and we want to go to the discrete time domain, so the digital sample domain. The way we do that, there's several methods. The easiest one is to discretize using the Euler method. The Euler method says that we can approximate derivatives by a first-order approximation, letting that dx by dt is approximately equal to the difference in samples. So, for example, dx by dt is x at sample n minus x of the previous sample, n minus 1, divided by t. And t is the sampling time in seconds. So this is the discrete derivative, essentially. T is the sampling time in seconds, and t is also 1 over fs, and fs is the sampling rate in hertz. So what we then need to do is for dVout by dt, use this expression for dVout by dt, plug that in, and also make sure that Vout is then sampled and Vin is sampled. So combining all of that information gives the difference equation, which we can then straightforwardly implement in software. So we have Vout sample n, so this is the latest sample, is this constant over here, or this coefficient, times the latest input sample, plus a different coefficient times the previous output sample. Now I've written it in terms of alpha, and alpha over 1 plus alpha, and 1 over 1 plus alpha, because these are reoccurring terms, and alpha actually is 2 pi times the cutoff frequency in hertz divided by the sampling frequency. If you remember, for RC filters, the cutoff, or the minus 3 dB point, is defined as Fc is 1 over 2 pi RC. So instead of using resistors and capacitance values, I'm just using a cutoff frequency because, it doesn't really make sense to do that in digital domain. So alpha is 2 pi Fc over Fs, and we can use that, and that gives us a first order low pass filter. I can use MATLAB or Octave, which is the free alternative, to plot the frequency response of my discretized filter. So let me do that now. What I need to enter is my sampling rate, which is 48 kilohertz. Then I can convert that to a sampling time or sampling period, which is 1 over the sampling rate. I need to load a package called control because I want to work with the Z transform. Now the Z transform might be intimidating if you haven't heard of it before, but I have a video on my channel. Again, I will be leaving a link in the description, which goes over the practical applications of the Z transform. Using the Z transform, I can convert this difference equation into a transfer function in the Z domain. Before that, however, we need to define alpha, which is again 2 pi times the cutoff frequency, which I'll select to something like, let's say, a kilohertz, divided by my sampling rate. So I store my variable fc, and I compute alpha. So once I've taken the Z transform, this is my result, and then I can plot the frequency response by typing in bode of my transfer function. So you can see here we have a low-pass filter. Low frequencies are relatively unaffected with a gain of 0 dB, which is a linear gain of 1. And once we reach our cutoff frequency of a kilohertz, we drop down by minus 3 dB to somewhere over here. And then we have a slope down, and high frequencies are attenuated by about minus 20 to minus 25 dB up to our Nyquist limit, which is half the sampling rate. So not the greatest low-pass filter in the world, so we have pretty bad attenuation in our what is so-called a stop band, and a very, very slow roll-off. The phase isn't too interesting in our case, but we can see that this actually adds lag into the signal later, and we'll see that when we do some tests. We'd also like to look at the high-pass filter, and it's exactly the same procedure as with the RC low-pass filter. We have our analog RC prototype, which in this case, the R and C components are interchanged. We're taking our output voltage across the resistor, and we have our input voltage feeding into the capacitor. Going through the differential equation, discretizing, this leads us ultimately to the following difference equation, and that's what we're interested in. This is then what we can implement in software to give us our high-pass filter. So now we can move over to STM32 IDE and implement these difference equations. So here we are back again in STM32 IDE, and I've already written the low-pass filter for us. The way I like to do it is have a header file and a corresponding source file or .c file. I'll have a struct which contains my filtered output, my filter coefficients, which I'd like to pre-compute to save us processing time when we have to do this in real time, and our sampling frequency. Then I have 3 functions. One is to initialize the low-pass filter, so we take the struct by reference, the cutoff frequency we desire, and the sampling rate of our system. Because we'd like to change filter parameters on the fly, I also have this set cutoff function, which allows me to change the cutoff frequency and recompute these filter coefficients on the fly. And that simply takes the new cutoff frequency as an argument, and of course the struct. Lastly, and most interestingly, the update function is the function that gives us a new output sample when we pass it an input sample. So going over to the .c file, our initialization function simply stores the sampling frequency and then computes the filter coefficients by calling our other function, which we'll go to in a second, and also resets the filter output to be defined at 0. The set cutoff function takes, of course, the cutoff frequency we desire in hertz and then computes the filter coefficients as per our difference equation. It's important to, of course, clamp the cutoff frequency because someone might be able to type in, a cutoff frequency that is higher than Nyquist limit or negative cutoff frequency. So I'm just doing simple checks here to make sure the cutoff frequency is within range. Remembering back to our first order low-pass filter, this is the difference equation we want to implement. And for that, the coefficients, because we don't want to recompute these the whole time, will be alpha over 1 plus alpha as our first coefficient, and 1 over 1 plus alpha for our second coefficient. And of course, alpha is defined as 2 pi fc over fs. And this is exactly what I'm doing in STM32 IDE. I have 2 pi, which I have here as a constant. Of course, I could make this nice as a define or something like that, times the cutoff frequency divided by the sampling frequency. So it's 2 pi fc over fs is our alpha, and I can use that to compute my coefficients. Remember, the first coefficient was alpha over 1 plus alpha, and my second coefficient was 1 over 1 plus alpha. Again, I can call this set cutoff function when I change, for example, my potentiometers on my final board or my final effects pedal to then alter my frequency response of my filter in real time. Once I've set up my cutoff frequency, of course, I can then call my update function, which actually gives me the filtered output or performs this IRR filtering. We wish to perform filtering using this difference equation, and again, that's all we have to implement. So our newest output is our first coefficient, which is alpha over 1 plus alpha times our newest input, passed over here, plus the other filter coefficient, the second filter coefficient, times my previous output. And I assign this to be my new output. Then, of course, I'm clamping my output, and in this case, I've made sure that my output is between -1 and +1. So this is my clamping over here, and then I simply return my filter output. And as you can see, it's an incredibly simple routine, and this can run very easily in real time. In main.c, I simply have to define my low-pass filter struct, which I call lpfilter. I need to initialize my low-pass filter, and for now, of course, I could do this with defines again, and I'm sorry for this rather crude implementation. I pass my struct by reference, I pass my initial cutoff frequency, which I'll set to 1 kHz, and my sample rate, which I've had as a define, and that's at 48 kHz. Then all that is left to do is in my process half function, which processes half of my double buffer, is on the left channel, which because we have a mono system, once I've read in my newest sample, I need to feed that into my low-pass filter by passing the struct and my newest input sample, and of course, this function then outputs my output sample. Then I put that in my output buffer and send it to the codec. And that's really simple, and I can flash this directly to my board. So I'll go up here, click play. I have my serial wire debug connected, and this will upload the code to my STM32F4 microcontroller. There we go, download verified successfully. And now let's use the Digilent Analog Discovery Pro to analyze the system before plugging this into a guitar. So this is the setup that this is running on. I have my Digilent Analog Discovery Pro. I have 2 oscilloscope channels, one to measure my input to the system and one to measure the output of my system. And I have this one signal from the WaveGen out connected as a frequency or function generator to test my system and perform some analysis. I have a very simple, not the greatest power supply, which provides 9 volts to my input. And I have everything hooked up here. You can see the board is on and running. I have all my probes connected and my serial wire debug connection as well. So let's use the WaveForms software to test this device and see if the filter is doing what it's supposed to. Digilent was very kind to send me one of these Analog Discovery Pro 3450 mixed signal oscilloscopes, and it's even more than an oscilloscope. It has 4 channels of oscilloscope, 2 channels of a function generator, and various other goodies, for example, logic analyzers and so on. And this connects via USB or Ethernet to your computer. And this I'll be using with the Digilent WaveForms software, which is essentially your PC-based oscilloscope. So starting up the WaveForms software, it's recognized my ADP 3450. I can simply click select. And then I have all of these functions over here. So scopes, wavegens, voltmeters, loggers, and loads of stuff which I still have to explore. What we'll be using is the scope and the wave generator to do, for example, time domain analysis. And we're using the network analyzer to give us a frequency response plot. Lastly, on the note of making this filter variable, I'm reading my control settings. So once I have a flag from my ADC, that is the control settings ADC, I'm reading the control settings in, applying a small deadband, and if the control setting has changed by more than 10%, I'm readjusting some sort of parameters. And this is one for the output volume and one for the control setting for the cutoff frequency of the low-pass filter. We also have a third potentiometer available, and we'll be using that for the high-pass filter cutoff, which we'll see after we've analyzed the low-pass filter. So here now in the software, I would like to use the network analyzer first, which I can use to give me some sort of frequency response analysis. So I'll click on that. On the right here, I can choose which channel to analyze, and I'm on channel 2, which is my output of the effects pedal. I am using a 10 times probe, so I need to set my gain to 10. My source is the WaveGen channel 1, and I would like to, because we're in the audio range, go from 20 Hz to 20 kHz. Of course, you can go a bit lower and a bit higher just to see the full frequency response. But now I have my potentiometer for my control set to right in the center. So if I click on run, I can start an analysis. And you can see at low frequencies, because we have a low pass filter, the signal is relatively unaffected. We're at about 0 dB. Now I haven't quite centered my volume control, so it might be a bit around 0 dB. And now the analysis is complete. At least one of them I've clicked on stop, and you can see we have our passband here, which is relatively flat, and then we have a slow roll-off as we saw in Octave or MATLAB. Now keep in mind, this is not with a 1 kHz cutoff frequency. I've played around a bit with my cutoff frequency control using the potentiometer, so we can vary this. So if I change the cutoff frequency now, just using the potentiometer, and then re-click to do a single measurement. So I've moved my cutoff frequency quite a bit lower now. I can use this measurement tool to find the -3 dB point. Now keep in mind, up here I'm at about 0.4 dB, so it's -3 dB down from that. It's about -2.6 dB, and that's at about 1.1 kilohertz. Now let me just readjust my potentiometer and do another measurement. And now I've adjusted my potentiometer, done another reading, and again I can find my -3 dB point, so it's about 800 Hertz, and of course I can turn that the other way as well. And here you can see the cutoff frequency has moved. So again, -3 dB from here, so -2.6, somewhere over here, and it's moved to 6.3 kilohertz. So we've verified we actually have a low pass filter, but we've also verified that we have a variable low pass filter. So we can change the cutoff frequency simply by changing the potentiometer. One thing we also need to verify is if the volume control works. So now we have the volume control centered at about 0 dB. And I see if we can get a little bit of boost out of it. Click rerun. And you can see we've got a boost of about 3 dB now. And of course, we can do also attenuation with our volume control, and we have a cut of about -11 dB. So that seems like it's working. We have a variable low-pass filter, even though not a great one. It's a simple first-order low-pass filter. We've done a pretty bad approximation with the Euler method, and we have a working volume control. Now we can implement the high-pass filter in cascade with this low-pass filter, essentially forming a very simple band-pass filter. So now we can try, after we've analyzed this low-pass filter at least a tiny bit, we can move over to the first-order high-pass filter. And it's exactly the same procedure, except that we're now implementing this difference equation. The way I've done that in STM32 Cube IDE is then simply take my low-pass filter header and source files and change them a tiny bit. For the high-pass filter, because of the difference equation, we also need to store the previous filter input, so I've added that to the struct, but other than that, the header file is identical. Going to the .c file, we also have to reset the current output and the previous input, so I've added that here, and we have to change the filter coefficient calculations. We only have one filter coefficient, and this is 1/1 plus alpha. Then we have this difference between the current and the previous input sample, and we're adding the previous output sample to form our output. Compute and store my filter coefficient, and then I compute my output here in the update function, simply using the difference equation, and then storing my previous input, same as before. So I've uploaded that code already to my board, and we can go back to WaveForms with the Digilent Analog Discovery Pro to test it out. With the controls pretty much centered, I can run a single measurement, so I have my low-pass filter and my high-pass filter engaged, and try to match my mid-band gain to about 0 dB. And you can see over here, since we've added the high-pass filter, now low frequencies are affected by the high-pass filter, which only allow high frequencies, and up here we have the low-pass filter, which affects high frequencies. So effectively we have a bandpass filter by cascading a low and a high-pass filter. The way I've actually cascaded these filters is I take my input sample, which is my raw data, pass it through my low-pass filter, and then pass that filter data through my next filter. Now keep in mind the order really doesn't matter for these linear filters. I could do my high-pass first and then my low-pass. Either way, doesn't really matter. So it looks like we have variability in our low-pass and high-pass filters. They're both working essentially at the same time by feeding into one another, and we have volume control. I'd also just quickly like to look at the time domain behavior, so to see if we have any phase lag, if we can match amplitudes, and so on. The way to do that with this WaveForms and the Analog Discovery Pro is to go back to the main workspace, and we are going to use the scope and the WaveGen. So the WaveGen lets me generate arbitrary signals. In this case, I just simply want a sinusoid. Let's just say 1 kilohertz of an amplitude of 1 volt. No offset. I can click run, and then I need to go back and look at my scope, which is over here. And then I need to click run on that. Channel 1 is my input, channel 2 is my output. So if I go here, if I play with my volume control, you can see it's going in steps. I can change my volume like so, and of course I can change my cutoffs. So if I change my low pass filter, so you can see I'm decreasing the cutoff frequency of my low pass filter, and that's giving me more attenuation at this 1 kilohertz. Or of course I can move it back again, and you can see I'm getting less attenuation. You can see also my yellow trace is my input, my blue trace is my output, and you can already see this phase lag or this delay. And this of course is what we expect when we filter a signal. We haven't looked at the phase response in detail, but we will have some sort of phase shift, especially if you move higher in frequency. So there's many more things I need to explore with this waveform software, as well as with the Analog Discovery Pro, and I'm sure I'll feature this in many videos. So far, it looks like our high pass and low pass filters are working, so let's move over, plug in a guitar, and see how this sounds. So I'm using my Eddie Van Halen amplifier, and straight from my guitar over here, plugged into the pedal with the high pass and low pass filters we just created, and into the amplifier. So let's try out the volume controls, high pass and low pass filters, and just have a little play around to see if it works. So here the effect pedal is now off. If I turn it on, all the controls set it to 12 o'clock. So the first thing I'll try is the volume control. And bringing it back to 12 o'clock. So this is the low pass filter. Let me try that wide open. So I'm increasing the cutoff frequency and turning it down. You can see it's really cutting off those high frequencies. I can turn it down even further. It's very dull sounding. I can open that up again by increasing the cutoff frequency. I do the same thing with the high pass filter. So right now it's at 12 o'clock. I can let loads of low frequencies through. I'm going to increase that. And the high pass filter is cutting out all of these low frequencies. So it seems like our little effects pedal is doing its thing.